Hello and welcome. This is section 1. It's a very brief video. If you're just tuning in, this is part of a larger playlist for chapter 19. I covered the organic chemistry textbook published by Klein in my class. So thanks for watching. Here we're talking about electrophilic aromatic substitution, chapter 19, section 1. Now, electrophilic aromatic substitution is sometimes abbreviated by me as EAS when I'm writing things down, and you might do the same if you're taking notes. Now, we've learned previously that ordinary alkenes like cyclohexene will react with things like bromine, and this is an addition reaction where the two bromine atoms add to the alkene in an anti-fashion. That means one bromine is on a wedge and one bromine is on a dash. And for this trans 1,2-dibromocyclohexane, we also form the enantiomer, which I won't draw. Now, benzene, we've learned, has an extremely stable structure because of this criteria that is met. We have a cyclic system, it's planar. We have 4n plus 2 pi electrons. And so this does not react with bromine in the similar way to add the bromine atoms, say, onto the carbon-carbon double bond on the right. Now, the reason why is because we're losing that resonance stabilization from the aromatic ring. So I'll draw a big red X through this reaction. This does not occur, okay? Instead, what benzene does is it does substitution reactions, and the end product still has that benzene ring, the phenyl ring with the 3 double bonds. These are some reactions that we'll learn in this chapter coming forwards. We have electrophilic aromatic bromination. We're basically just substituting this hydrogen for bromine, and we still have those 3 double bonds. This is an electrophilic aromatic chlorination, and we'll learn all of the different reagents for these. This last one is an electrophilic aromatic nitration. In the nitration reaction, we install a nitro group. The nitro group, I'll draw the Lewis structure here in case you're kind of seeing this for the first time, is a strange looking kind of structure because there's a formal charge of +1 on the nitrogen atom and a formal charge of -1 on the oxygen atom, and it kind of looks like a deprotonated carboxylic acid, so there's resonance there that you can draw. In this top right reaction, we have an electrophilic aromatic sulfonation, and this is a sulfonic acid group. It's kind of acidic like sulfuric acid, or H2SO4, okay? So that's a full sulfonic acid group. And so I'll draw the Lewis structure here for you in case you're kind of wondering what that looks like, in case you're seeing this for the first time as well. So it looks a bit like sulfuric acid, but instead of an H on the left, we have a phenyl group on the left, okay? So that's benzene sulfonic acid. Here we have 2 reactions that are similar. We're creating carbon-carbon bonds, so keep an eye out for these 2 reactions when they're covered. In this first reaction, we're installing an alkyl group, so this comes from a Friedel-Crafts alkylation reaction, and in the second reaction we're forming an acyl group, and this comes from a Friedel-Crafts acylation. Acyl and acylation are new vocabulary words, but basically we're making a ketone, okay? So this is a ketone functional group here, okay? So keep watching and stay tuned, and we'll see all of these reactions coming up in the next few videos. Thanks for watching, and please subscribe.